It's I just tried to pick out some basic applications here and there. So there's a few things different. There is some compound interest in here. I want to finish this up. We've probably done all the basic types of problems with compound interest, so I want to go ahead and look at this. So what I want to do on these is I want to set up example 1, let you finish, and then see if you can do example 2 on your own, because we've done this, okay? So I'm going to give you a little chance to do that. So this is your compound interest formula on here. So this says if an investment company pays 8.5% compounded quarterly, it says how much should you deposit now so that you'll have $10,000 in 5 years. And all these problems are all just, you got to know what I've given you, what you're trying to find, and then how to solve the equation. Okay, so let's start by writing this down as A equals P times 1 plus R over N to the NT. And let's see if we can get this put together then. Okay, so first of all, it says how much should you deposit now? So what is the unknown that you're going to have in this equation? P. Okay, that's the unknown. You don't know how much to put in now. That's what P is. Where does the 10,000 go? That's A. Okay, that's what you want in the future. So what goes there is you would have a 10,000 there. You would have P as this. Okay, and then in this, let's see, you have 8% interest. So you remember you moved the decimal back 2, so that's 0.085. And it's quarterly. So what does that tell you? N is 4. Okay, N is 4. Okay, all right, so we have that, it's over 4. Okay, then what we'll have here in the exponent is 4, but it also says 5 years. Okay, so this time right here, when you solve this equation, do you have to use logarithms to solve this equation? No, because your unknown is not in an exponent. So all you really have to do on this then is just do this. Okay, you just divide both sides by this big mess right here. Now, you don't have to show the step. I'm just saying that, okay, we're dividing by this whole thing. So what you want to do is we're going to do this mostly on our calculator. So P is going to be 10,000 divided by 1 plus 0.085 over 4. And you go ahead and do that to the 20th power. Whatever you can do in your head, just do in your head. Okay? So with that one, then we can go ahead and just do the calculator and see what we get. So there's no logarithms on that one because it's not an exponential equation. Okay, and then this one again, just let the calculator take over and do the work. So I'll go 10,000 and then divide by 1 plus 0.085 divided by 4 and then raised to the 20th power. Okay, just let it do all the calculation in one step at the end, so therefore you can round at the end. So that means the principal, round it to 2 decimals, that's what's logical when you're talking about money, would be $6,566.87. Okay, so that's how that goes. Okay, so that one is not an exponential equation, right? So now I'm going to let you try the next one. I'm not even going to do anything. I'm just going to give you a few minutes to see if you can do it. Get your calculator out and see if you can set it up and go through the whole thing, because we've done this before, and see if you can do that. You can look at your compound interest formula, see if you can get it set up and solved, okay? And I'll let you work on that for a few minutes before I do it. And one of the keys is always to know what's the difference between A and P. P is what you start with, A is what you end up with. And this one's got logarithms because it is an exponential equation. So you got to get your logarithms and get your calculator out and solve this. What's that?
Am I putting something in wrong spots?
What'd you say?
Am I putting something in for last one on my calculator?
That's an interesting answer. On the one I just did?
Yeah.
Okay. You did something wrong in there somewhere. Oh, because it looks like what you did is you didn't put the whole thing in, because I see answer to the 20th. Okay, now the only thing that's to the 20th power is this thing. You had to have put that in wrong. So you just want to put 10,000 divided by that to the 20th. Just do it in one step. Because I can't tell exactly what you did on there, but I think you did it in steps. Because I see that ANS to the 20, you may have done 1,000 divided by that thing and then to the 20th. That's not right.
Oh, I think I figured out what I did.
Yeah, I think you just do it in one step, and if you do it in one step, then you got a good chance. Okay, I wouldn't do it in steps. I just get the answer and then go to your calculator and get that figured out.
I think I put it as a percent.
Yeah, so that has to be what you did there. And one of the reasons I want you to do this problem, because I want to make sure at the end of the problem that you know how to do this in your calculator right, because I see students on this problem all the time mess up because of the calculator part. Not because of the math part, just putting stuff in your calculator. Does anybody have an answer?
2.72 years.
What'd you get? 2.7. I haven't worked it out yet. Anybody else get 2.7?
I got 2.7.
You got 2.7? Okay. I'll go ahead and set it up, and you can at least see if you got it set up right. So the way you should set this up is like this. You'd have 7,500 is equal to 5,000, and then you would have 1 plus, the interest is 15, so you got to have 0.15. Monthly is 12, and then you would have to the 12t power. So that's step one, is make sure that you understand how to set it up. Okay, we got that? Okay. Now, the mathematics behind this is this. You need to start by dividing both sides by 5,000. Do this. Okay, so now you're going to have 7,500 over 5,000 is equal to 1 plus 0.15 over 12 to the 12t. Now you're ready to do your logarithms. Okay, so when you do your logarithms, you're going to do that, and then you're going to bring down the 12t. Okay, and then the last step is I want to make sure you know how to do the calculator. I don't want anybody messing up on that. So we'd have ln 7,500 over 5,000, and then this is going to be equal to 12t multiplied by the natural logarithm of 1 plus 0.15 over 12. Okay, that's the mathematics. Now what do you do to get t by itself? Divide by this big thing. Okay, so you're going to divide both sides by 12 ln 1 plus 0.15 over 12. Okay, so now when you go to your calculator, you want to make sure and think about your answer. I mean, if you get something weird, then think about what's going on in the problem. So again, you got to do it like this. And I did a problem like this before, so you have to go like this. You have to go ln 7,500 divided by 5,000, close the parentheses, that gives the numerator, whoops, don't want to do that, so get that, divide by, then what do you got to do? Parentheses, you have to have parentheses because you have 12 times something. Okay, don't mess up on that. So you got 12, I just messed up, parentheses 12, and then ln 1 plus 0.15 over 12, and then close the parentheses like that. Okay, now let's see, what did you say, 2.7? Okay, that's it. Okay, 2.7. Okay, so you would end up having, time would be about 2.7, and you assume this is in years. And the reason you'd make that assumption is because that interest rate is annual, but it's compounded monthly. That's where that comes from. Your interest is always an annual rate, but it can be compounded at different amounts at different points in time. Okay? All right, that's all I'm going to do on compound interest. Okay, I think this next problem has to do more with, I think, compound. No, this is continuous. Now this is one more. Okay, all right, one more. Then we're going to talk about continuous compounding. Okay. So this one right here, we want to see if we can set this up. So I'm going to go ahead and write the formula down. To me, that's a good way to start. So you have A is equal to P times 1 plus R over N. I'll write it the way they do in the book. I think different books do it different ways. So our book does R over N to the NT. Okay? Now, in this particular problem, the reason I want to do this, when I did a problem like this similar a little while ago, sometimes students think something's missing. I didn't give you the principal. I didn't give you anything with that. I didn't give you any money on this. All I said is your money is going to triple, and then I did give you that, I did give you the interest rate, and I did give you compounded monthly. I don't have to give you any money on this, okay? So here's what you do. You pick anything you want for P except 0. Don't use 0, okay? How about 1? If that's 1, what is that? 3, good, okay? If that's 10, that's 30. But to be simple, use 1 and 3. If it was a doubling problem, you'd use 1 and 2. So there is nothing missing because it doesn't matter. So we're going to put 3 there, 1 there, and let's see, our interest rate is 0.105. We're compounding monthly, so again, that's divided by 12. And then that would be to the 12t power like that, okay? Yes?
On the exam, are you going to provide us with these equations? Or
Am I going to put what?
Are you going to provide us with these equations? Or
Yeah, I'll provide you the formula.
Okay.
Yeah, I'll give you the compound interest, and I'll give you the continuous compounding, those kind of things like that, okay? All right, so the answers, you want to do like Jeopardy? I give you the answer and you give me the question. That would be a great way to do the test.
Oh.
That's not what you had in mind? I don't know. That might be an interesting thing to do. Okay, well, let's do the ln of both sides. So now we do ln of 3, and then we have ln. See, the 1 is not really necessary. Then we have 1 plus 0.105 over 12 to the 12t power. Okay, so now what you'd have is ln 3. Again, bring down the 12t, so you'd have 12t times ln 1 plus 0.105 over 12, and then divide both sides by that quantity again, and then you'd get your calculator out to get the final answer. Okay? So what you'd end up doing is, again, you got to put that parenthesis around the denominator. That's something to make a note of and make sure you don't mess up on. So let me put that in. Let's see what we get then. Okay, so it looks like I'd do ln 3, close parentheses, divide by new parenthesis, 12, ln 1 plus 0.105, and then divide by 12 like that. Double up on the parentheses, and that'll give you about t is equal to about 10.5 years is how long that would take, okay? So whenever you're doing like tripling or doubling, I don't have to give you the original amount of money because it doesn't make any difference. The thing that happens on this is if you started with a penny, it would still take 10.5 years for that penny to change into 3 cents. Okay, it doesn't make any difference. Okay, does that make any sense? It sounds kind of weird, but that's the way it works. Okay, it takes $1 million to go to $3 million in the same amount of time. That's how exponential equations work. Okay, the next thing is continuous compound interest. This does have a mistake on it. I just saw that. So it's not that, it's A equals PE to the RT. That negative shouldn't be in there. That's continuous compound interest, okay? I always think of PERT. It spells like the word PERT. Then I think of shampoo. I don't know why, but I just do, okay? So I think of this as the PERT shampoo formula. Okay, that's one of the ways that I remember this, okay? So what we're going to do with this is actually a very similar problem to the one I just did, is it says a population's growing at this rate, compounded continuously. Now when it says continuously, this is the formula you have to pull out. So when you get to your next exam, if I do a problem like this, okay, I would give you the formula, but you'd have to know which one it is on a formula sheet, okay? So let's write down what we have. We have A equals PE to the RT. Okay, and again, the rate is going to be 2.3%. Okay, I didn't give you the principal, so we do the same thing. Now this time we're figuring out how long it takes the population to double, so just put a 1 there and put a 2 there. So what you would have is the equation 2 equals 1 times e to the 0.023 times t. Okay, this is a little bit less work than the last problem, so you have 2 equals e to the 0.023t. Okay, now you're ready to do log of both sides. You would do natural logarithm because it's better because of that e. So we're going to do ln of both sides for that reason. Okay, so now what we'll have is ln of 2 equals 0.023t times ln of e. Okay, for the fourth time, what's ln e?
1.
Okay, good, okay. That shows up all the time when you're doing this stuff, and it'll show up in higher math a lot too. So now what you do is you divide by 0.023, and then you're ready to go to your calculator, okay? So that's how that goes, okay? All right, and then what we would have from here, just get the calculator out, and then we'll round off to a decimal or something like that. So I just go ln2, and then divide by 0.023. Okay, so that will give about 30.1 would be approximately the answer on that in years. Okay, that's the idea. Okay, so that'll pretty well wrap up the continuous and compound interest stuff. We're going to kind of transition now to a different type of application of exponential equations. So I've done a lot of those things. You want to be sure that you know how to do that, those kind of problems. Okay, here's the next thing I'm going to look. I'm going to look at two examples kind of on this. And this is like in biology, the populations tend to do this. Like if you had a petri dish and you just had some bacteria in it, okay, it tends to just goes out of control. Now, it doesn't go out of control forever. Okay, the universe can't fill up with bacteria, but it accelerates for a while, then there's no room left, so it tends to level off. So we tend to model populations with exponential functions, at least for the first part of it. There's another kind of model we call logistic, where it will do like this. It'll accelerate, then it'll level off. That's called logistic. So we're going to talk about that tonight also. So the general formula for growth of cells, I just picked out this particular problem. So n naught is just the initial number, like this says. So that's what you start off with. N is afterwards. Okay, after a certain amount of time, you have that number of cells. Now, to me, this is the continuous compound interest form. It's the same thing. So what you have is K is a rate, a growth rate, T is time, and then you have E. So if you look at this particular example, this says that you have N bacteria at a time T, and uninhibited growth means it's going to grow forever and the universe is going to fill with bacteria. That's what I mean by that, okay? So if you want to figure out the answer to part A, you either know it, which I would hope you do, or you figure it out. Okay, if you don't know it, you would do this. You would just do in 0 hours, you would just replace T with 0. So you'd have 1,000 e to the 0.01 times 0. So that would give 1,000 times e to the 0. So what is that? Anything to the 0 is what? 1, right? Okay, so you would end up getting 1,000 times 1, so the answer to that problem is 1,000 cells. Okay, now you didn't have to do that because that's built into the problem. And when t is equal to 0, that number right there in an exponential equation is the starting point. So you could automatically know that that's 1,000. If you don't, you figure it out. Okay, all right. Now the growth rate. The growth rate is the coefficient of t. So that's going to be 0.01, or in a percent form, we would say 1%. So it's a 1% growth rate, okay? All right, now what we're going to do is we're going to graph this. So you want to get your calculator out for this. I wouldn't expect you to do this without your calculator, okay? And I've kind of already put a window on here that I want you to put in too. And one of the things I want to do with this problem too is show you that you can also solve some of these problems with your calculator. You can use technology to do this also. Let's see, Calc 2, I was doing sequences this morning, so I need to get in the right mode here real quick. So, okay, don't pay attention to what I'm doing. I just need to fix this. Now I'm fixed, okay? Now, let's just put this in, okay? So let's put in like this, 1,000. Put in the 1,000, then you put in E, so you go second ln to get E to come out. Then you put 0.01, just do your variable key to put the variable in. So you have 1,000 e to the 0.01x like that, okay? Now what you're going to expect to happen on this is the graph is going to start at 1,000, right? Then it's going to exponentiate like that. So what I did is I kind of played with this a little bit, put this window in. I wrote on here what I wanted you to do. I want you to go 0 to 200 on X. Go ahead.
Did you do anything for time?
Could you do what?
Did you put anything in for time?
I put X in, I think. I hope I did.
Oh, okay.
Yeah, I did. Okay, I can barely see that. Yeah, you just put in the variable X, okay? All right, now for the window, let's go 0 to 200. Okay, you just got to figure this, play with this a little bit. Let's scale by 50. Just follow what's on your handout. And then for the Y's, let's go 0 to 6,000. Okay, and then let's scale that by 1,000 like that. So if you get that put in, what you expect, the one thing you want to understand on there is your Y value has to be above 1,000. Okay, that's what you have to know so you don't waste a lot of time figuring out your window. So it's going to go something like this. So what it's doing is it's exponentiating, it's getting out of control, and it usually gets out of control pretty fast. If you took that out a little bit bigger, you know, from 0 to 200, it would just start turning up real big real fast. Okay, so let's just make a sketch of the graph, and this is what I would want you to do for the purpose of a sketch. You do want to label everything, so T is time in hours. Okay, so you want to put that on there, and then the y-axis on here is, this would be in, and then you want to write that that is the number of cells. Okay, so you do need to get that on there, because if you don't put that on there, then nobody's going to know what you mean by anything. Okay, and you got to put your values on here too. So let's go out like this. Let's just go 50, 100, 150, and then 200 like that. That's the way we chose to scale the x-axis. And then the y-axis, let's go up to 6,000. So 1, 2, 3, 4, 5, 6. Now you can put 1K, 2K, and so forth like that if you want to. Okay, then I'd know what you're talking about. Okay, so for this problem, I would say 3 good points. Okay, if I have you do this on an exam using your calculator, I want you to have at least accuracy with 3 points. Just use your trace. So I'm going to go trace 0. I already know what that is. That's 1,000. That's built into the problem. So you have a point 0, 1,000. Pick another point. Let's go to 100. So I'm going to trace at 100. And that would be about 2,700. Just estimate it best you can. So that's pretty good there. And then we might label that as 100, 2718. You can round it if you want to a whole number like that. Then let's trace at 200. That'll give us kind of the end point of our graph. And then that's about 7389. So I'll just go up kind of like that. So let's see. That's up a little too high. Did I go out all the way? Yeah, that's fine. Okay, so let's just go out to maybe add another notch and just put it up there, okay? So that's going to be 200 and then 7389 like that. Then you can sketch. So if you've got like 3 good points labeled, then you've got a pretty good sketch, okay? One of the reasons I want you to do the graph on this, because some of these problems I'm going to show you how to answer the problem totally with technology and not with algebra necessarily, okay? So if you want to find what the population is after 4 hours, you have 2 choices. One thing you could do is you could just do n of 4. So you could take your function and just do 1,000 e to the 0.01 times 4, okay? And you could do that on your calculator, but the fast way to do it is this. Just trace, just type trace, type 4, and then that'll give you that after 4 hours you have 1,040, and then maybe you have 81% of another one divided, probably not. Just use a whole number, okay? So it doesn't matter which one you do. You could either use that or you could say 1,041, okay? So that's kind of for all practical purposes. We could go through and just trace on our calculator to get that, okay? Now what I'm going to do on this next problem is I'm going to show you 2 approaches to solving this. The first thing this question says is, when will the number of bacteria reach 1,700? So remember, your formula is n of t equals 1,000 e to the 0.01 t like this. So what you're going to do is, what are you going to plug in for n? 1,700. That's what the problem says. So what you'll do here is you'll do, and I'll move this up a little bit here, you'll just do 1,700 is equal to 1,000. That will be e to the 0.01 t, like that. Now that's the same kind of equation we've been working on all night. So you would just divide by 1,000. Okay, and it's not a bad idea to just calculate that out. If you did 1,700 divided by 1,000, that's 1.7. So I don't mind. You can do that if it turns out to be a whole number or a decimal stops. But if this decimals go on forever, you probably ought to wait till the end on that. Okay, then this is going to be e to the 0.01t. Then we'll do an ln of both sides like we've been doing. So you would end up having ln of 1.7 is equal to 0.01t times ln e. And ln e is 1. So then if you just divide by 0.01, then you would get approximately what that answer is. I'm going to show you another way to do this problem on your graphing calculator, though, in just a minute here. Okay, so let's see. If I do that, if I just do ln 1.7 and close the parentheses and then divide by 0.01, then that should give me the approximate answer on this, as it takes about, and I can't remember, this is probably hours. Yeah, this problem's in hours if you read it. So that would take about around 53 hours is how long it takes for that to happen. Okay, all right. This is not a perfect model, but it's a reasonable model for cell division. Okay. So the other thing I want to show you is you could do this problem 100% on your calculator by doing this. And if you got your calculator out, just do this with me so you know how to do this. What you could do is you got this graph, then you could go to y equals, and then you just put 1,700 in. So if you put 1,700 in, all that's going to do is give you a horizontal line, right? Okay, so if you graph that also, then what you're going to have is this. Now, we've done this before. You just need to figure out what that point of intersection is, okay? And then that will give you the same answer. So you can do it this way also. Graphically, what you can do is go second, trace, then go to option 5. Okay, so if you go down to option 5, intersect, when I press enter, 2 cursors will come up. That's the first cursor. You can kind of close it in close to the intersection point and press enter. A second one will come up. Just press enter again. When it says guess, press enter again. Then it'll come out. So that's the answer we got, was 53, see? Okay, so you can do that with technology using your graphing calculator. Okay, everybody with me there? Okay, all right. Okay, well, let's do this next problem. We've already done this, but I again want to show you how you could do this graphically. Okay, so we're going to do this next problem graphically. Okay, so I'm going to erase that thing right there. So if I wanted to do this graphically, what would I put in for y2? 2,000, because the problem says how long does it take to double, right? So we've already done how to do this algebraically. So if you did this graphically, you would just put in 2,000, graph it, and you do exactly the same thing. So you can analyze this graphically like this. Then you would just go second, calc, option 5, intersect, do exactly the same thing. Press enter, enter again, and if I did that right, out pops the answer. Okay, so what you'd end up having on this is graphically, by the graph, you would end up having about 69.3 hours. Okay, so you can do that either way. I want you to actually know how to do that both ways. Okay, all right, everybody with me on how I did that graphically, intersect and that kind of thing? That's a nice thing to know how to do. Okay, so that's exponential growth. Exponential growth is what you would expect from cells. They get bigger over time. We also have what you call exponential decay. Exponential decay just means the graph starts big and it gets smaller. Okay, there's all kinds of things that do that. One of the classic examples is radioactive dating. So if somebody finds a bone or something that has a certain mass, we can measure how much radioactive material is still in that bone, and we have to predict how much was there in the beginning, but we can do that based on the size of the bone. Then we can use this model to figure out approximately how old it is, okay? So what we're going to do with this is we're going to look at a problem with exponential decay, all right? So with this one, what makes it decay is the fact that that number in front of t is negative. If that number is positive, it makes it grow, so that's why it's a decay function. So this is a radioactive isotope of iodine-131 that can be modeled by an exponential function. And all these things, like carbon-14 has a certain function to it, has a certain rate, decay constant to it. So we use different isotopes for different types of dating things. Okay, so first of all, in this particular problem, the rate is what I highlighted. So the decay rate on this would just be negative 0.087. Or if you wrote that in a percentage, you don't have to put the negative on there. It would just be about 8.7%, but everything is decaying. Okay, you can put the negative on there if you want to. It doesn't make any difference. But that would be the rate that this thing is decaying by. Okay, so we're going to do this problem also. A lot of what we're going to do on here is going to be done graphically. So let's go ahead and put this in so you can kind of see what happens on this. So the first thing you got to do on this is, I said the initial substance has 200 grams. So that means that's what A naught is. So what you're going to graph is you're going to graph A of T equals 200 and then e to the negative 0.087 t. So you want to put that in your calculator. Use the viewing window that I put on your handout. Okay, so let's get that in, 200. And then e raised to the negative 0.087 times x, okay, like that. Okay, now let's put the window in. Now the way that I figured out this window is like this. So you need to know this when you're doing a test or something. This thing is going to start at 200, and it's going to go down. So notice my window, I used 0 to 300 because I knew what was going to happen. You need to know the same thing. Okay, so when we put the x in, let's go 0 to 30 this time. Okay, a good scale on that might be like 5. That's a good way to scale that. Then we're going to go 0 to 300. And a good scale on that's going to be 100, like that. Okay, now if you type graph on that, you should see a function that's going to start at 200, and it's going to decay towards the x-axis. Okay, so let's make a sketch of the graph on here. Okay, and again on this, t is time, and let's see, it says in days. That's important you put that on there, so I know what that is. And this is going to go to 30, and we can go 5, 10, 15, 20, 25, 30 like that. So you can just label kind of like that. The y-axis is going up to 300. Okay, and then what we're doing on this is going to be the amount. And does it say anything like grams or anything? Yeah, it says grams. So this would be the amount. And you'd want to say that that's in grams. Okay, those are things you need to put on your graph. Okay, again, we just trace out like about 3 points. Okay, so the first point, we already know the first point's at 200. Then I would trace at 30, so I just type my trace button, trace out at 30, and label what that point is. So that point right there is about 30 and about 14.7. Okay, let's get one more. I don't care what it is. Let's trace 10. Okay, so we trace 10. That's going to be 10 about 83. So just kind of approximate that as 10 and then maybe 83.8. And then you can sketch like that. So now you've got a good sketch of your graph. You've got everything I need to see. Everything's labeled. You've got 3 accurate points that are labeled. That's good enough. Okay. So what we're going to do with this problem is we're going to do a lot of this on the graphing calculator. So the next question is, how much iodine is left in 9 days? Well, you have 2 ways to do this. You could just do A of 9. So you could go back to your function, which is here, and you could just do 200 e to the negative 0.087 times 9. Okay, you can do it that way. You can get your calculator and do that if you want to, or you can just do this. You can just trace at 9, and that'll tell you the amount that's left there. See, this is decaying, so on the graphing calculator, that's going to give you about 91.4 grams. So it's a little quicker once you get your calculator, your graph done, to solve a lot of these problems graphically. Okay? Okay, now the next thing it says is, when will 70 grams be left? So you have 2 ways to do this problem. The first way you could do this problem is you could just replace that A with 70, and you would have the exponential equation, 70 equals 20, e to the negative 0.087t, and solve it. I feel like I've done that problem like about 10 times tonight, right? I have done it a lot, so I'm wanting to focus a little bit more on how you would do this problem graphically. So what would you do graphically? Well, you go to y equals, and you would put in 70. Okay, and then you can look at for an intersection point like this. So if you put that in, what you're trying to do is you're just trying to see how long does it take for that y value to get to 70. Okay, so what you do is you do your intersect command, and then that way you can bypass the algebraic approach of this. So I just go second trace, option 5, intersect, just kind of enter. First cursor's good, second cursor's good, yes, and you'll always know you've done that right because it'll be blinking on the point you want it to be blinking on, okay? So that means that's going to be about 12.1. Okay, this says when will that happen? So this was in days, so it'll take about 12.1 days. So it's 12.1 days, gives you an amount of 70 grams, okay? So you can do it graphically like that if you want to, okay? Okay, now the half-life. Let me talk about what half-life is, okay? So this is kind of a big deal in radioactive dating. It's also a big deal in medicine. So particular medications have a half-life to them, which just means there's a certain amount of time for that drug to get halfway out of your body. If you started with 30 grams, there's an amount of time for that to decay to 30. That's a big deal in medicine. So what that would mean in this case is we could solve this two ways. Okay, you could do 200. You have 200 e to the negative 0.087 t, and the half-life would mean the opposite of doubling. That would just have to decrease from 200 to 100. So you could solve that problem with logarithms, or with technology, you just do this. Okay, so if I want to find the half-life, graphically I would just graph 100, and then you'd be doing the same kind of an idea here. So you can do the half-life algebraically or graphically. So now you just do the same thing. You go second trace, option 5, intersect, and usually just press enter after each cursor pops up, and then this will give me the half-life then. Okay, so if you look at what's on my calculator here, then it looks like that half-life is approximately 7, I'll just say that's about 8 days. So what that means is every time 8 days goes by, the amount cuts in half. And it's every 8 days it's going to do that. That's how exponential functions go, is that's how long it takes for that to happen. That's what we mean by half-life, okay? Everybody okay with what I'm doing? Any questions? Okay, all right. So this section I wanted to use a lot of technology on. Okay, so next thing I want to look at is just putting a problem together. Then I'm going to show you how to do regression equations on the calculator also here, and then I'll finish up with logistic growth here. Okay, so what this problem is saying is it's saying you're obeying the law of uninhibited growth, so immediately that means, hey, you got to get that formula out. Okay, that's a formula I'll give you, but you got to know what it is. Okay, all right, then it says 500 bacteria are present initially. So that means the 500 goes in for M naught. Okay, then it says, and there are 800 after 1 hour. So that's left over, and then the T is going to be 1. Then it says how many will be present in the culture after 5 hours. And then how long will it take until there are 20,000 bacteria. So you have to start this problem like this. You have to start by looking at this equation. You'll have 800 is equal to 500. And then e to the kt, well, k is 1. So those are the three things you've done. You've got to find k. I didn't give you the growth rate, but I gave you enough information to figure it out. And this is how in the real world you would figure out k, is you would just get some data, plug it in, and then you would be able to find what that growth rate is. So we need to solve this. This is an exponential equation. So I start by dividing both sides by 500. You could cross out those zeros and get 8/5 is what I'd do. Then I'd just have e to the k like that. Okay, this is a kind of a problem where you'd have to take the logarithm of both sides. Okay, so we'd want to do that. Again, the standard stuff is to bring the k down. So you would have ln of 8/5 is equal to k times ln of e. Okay, ln of e is 1 like we've seen all night. So that would end up giving you your k value like that. Now we're going to round this maybe to like 4 decimals or something like that. So I'm just going to take my calculator and do ln of 8 over 5. And we'll round that off to a certain amount. So let's just use 0.47. I like that. So that would be what k is. All right. So that's how you start the problem. So what we have now is the second thing you need to do is your function is n of t equals n naught. N naught was 500. That was given in the problem that you started at 500. Then you would now have e to the 0.47 t like that. Okay, so you got to start that way. If I don't give you k, you got to find it. Okay, now to answer these questions, then all you do is how many will be present in the culture after 5 hours? Well, then you just evaluate that at 5. So you do 500 e to the 0.47 times 5, and you take your calculator to figure that out. But what's different about this problem is you had to use the information I gave you to figure out what k is. So now I just put in 500, and then I do e to the 0.47 times 5, and then just round that off. So let's round this off to maybe 1 decimal. Or it's really, this is the number of bacteria, so it makes a lot of sense to just round to a whole number. So let's just say 5243. Okay, that would be the number of bacteria that you would have. Okay. Okay, so that's how that would work out. Now the next problem, I'm not going to solve the next problem because we've done it enough, but let's just talk about how you would do this. So if you're doing how long it would take for there to reach 20,000 bacteria, then you would do this. Okay, so on this next problem, you would replace that with 20,000. That's equal to 500 e to the 0.47 t, and you would solve that. Okay, so again, what the problem said is you started with 500, how long to end up at 20,000? Okay, that would be a logarithmic, you'd have to use logarithms to solve that. But I'm not going to finish that up because I want to show you how to do regression on your calculator. And then I'll talk a little bit about logistic to kind of finish this up here tonight. Okay. Okay, so let me show you how to do that, how to do just one example of regression. One thing that you'll see on the homework is you want to know these things like this. So for instance, if you have a set of data that looks kind of like this, that's going to be an exponential function. Okay, exponential functions tend to start off and then they curve up like that. If you see a set of data that looks like this, okay, that's going to be logarithmic regression. Okay, so the way that you do, if you learn how to do one, you can do both. Okay, so if you haven't done this before, you might need to write down the keystrokes of how you do this. So I'm going to go ahead and just have us do the regression on this, but don't do the last piece of data. Okay, because the question on here is you're going to do a regression analysis on your calculator and use that to make a model to predict what the population is as 2003. Okay, and this is the way we make predictions. Okay, this is exponential functions are typically used to model population. Okay, so here's what we're going to do on this. First of all, you want to press your stat button. Okay, the stat button is where we put in data, and then it'll highlight on one, then you press enter, then you got, this is where you put your data in. The first thing you want to look at is, do you have L1 and L2? Does anybody not have L1 and L2? Tell me, because if you don't, you need to fix it, okay? If you don't have L1 and L2, do this. If you're not sure, do this. Go stat, and then go option 5, setup editor. Okay, that'll fix everything for you. Okay, so here's what you're going to do on this problem. We're going to put a bunch of data in, then I'll show you how to get a regression equation. Now, you could do 1900, or you could do this. What I'm going to do, because the numbers are smaller, I'm just going to use 0, 10, 20, 30, and so forth. Okay, so what I'm going to do is I'm going to start at 0. Okay, and do that. Okay, now you could do it the other way too, it's just the numbers are smaller. So you want to go straight down your list, and in L1, just start putting these numbers in. Okay, all the way until you get to 2000, which would be 100. Okay, so we just keep putting everything in, 10, 20, 30. I think everything's going up by 10s. Whoops. Yeah, This thing is so hard to type on because I have to do it by my mouse. Okay, so I think I got all that data in. Okay, so I'm just choosing to do that by starting with 0 to 100. Then what you want to do is put the population in, and this is probably in hundreds of thousands, or that's probably more like millions. That's what millions is if this is U.S. population. So you just put the data in. You do 76.2. And let's see, then we got 92.2 and so forth. So go ahead and get all that put in. I should have given you a problem with 5 pieces of data instead of this. Okay, let's go. Almost there, 248.
We're having so much fun.
I know, I can tell. So we got that, and then the last one is, oh God, I messed up. Okay, that's the other thing I got to be careful about. 248.7. And then finally, I want you to stop here at the 281.4. Okay, so I'm going to show you what to do. Oh, got that wrong again. So 281.4. All right, and then I'm going to show you how to do a scatter plot. Okay, so what we want to do is once you get your data in, let's go to the window. And when you do the window, just put it in like this. Make X go 0 to 100. Make Y go 0 to 300. Okay, that would be a logical way to fit the data. So let's go again, 0 to 100. I would scale that by 10. Okay, like that. And then 0, let's go for the Y, 0 to 300 by 100 like that. Okay, so once you get your data in, the other thing that you want to do is this. So just fill in your window like that, and then do this. Go to Y equals, clear off anything you have in there. So if you got graphs from other problems we've done tonight, take it out. Then what you want to do is get your cursor blinking on plot 1, and then press enter. And what that'll do is that'll turn on the ability for the calculator to do a scatter plot. Okay, so now if you press graph, you just have that. So that's like the U.S. population modeled over those 100 years. Okay, so that's making an exponential curve. I think right now the population's in the 350 million range or something like that, and it continues to exponentiate. So what you're going to do, the next thing you're going to do is you're going to find an exponential equation that fits that data. You might want to write the keystrokes down on here if you don't know how to do this. So the first thing you do is you type stat. Okay, then what you do is you go to calc. Okay, you highlight that calc menu like that, and then you go down until you find the right regression equation. So if you wanted to do a exponential regression, find the one that says EXP regression. Okay, so just highlight that and then press enter. Okay, let me show you what happens. Okay, so that's going to do this. Now, everybody's calculator is a little different. You may have a different model than I have. So typically the default comes up is X is L1, Y is L2. Then go down, on my calculator, you go down to where it says calculate. Then you press enter. Okay, then you press enter again. And it'll give you a bunch of stuff here. Okay, it'll give you this. So the equation you get is Y equals AB to the X power. So that's a standard exponential equation. And then we're just going to plug in what we have. Let's just use 1 decimal. So A is 80.6. B is 1. Let's say 01. Let's just say 01 to the X like that. Okay. Now it's a little different on everybody's calculator, but if you get your data in and again go stat, calc, exponential regression, you'll do that. Now I think you'll do this on your homework. You'll also do a logarithmic regression. You'll do it like that. Now, the last thing I want you to do is do this, and you'll be amazed. So now we're going to put in 80, go to Y1 and put 80.6, parentheses, 1.01, close parentheses, raised to the x power. Type graph and see what happens. This better work. Okay. Okay, I don't know. I'm a little bit suspicious of that. I think all of my data's in there okay. Are you getting that? That doesn't seem very good to me. I was a little worried that maybe I put something in there wrong. And it may be that I rounded too much. But what's supposed to happen on this is it's supposed to fit the data in a statistically significant way that minimizes all the errors. It really should be a little tighter than that. So either I had one piece of data wrong on there, or maybe I didn't round enough. I probably just didn't round enough. Probably wanted to use a little bit more decimals, okay? All right, so does that make sense what it did? Okay, you learn a lot about this in statistics, how you model data with regression, and if you did this by hand, it would be a nightmare. Okay, so like years and years ago, people crunched these regression equations out by hand. Nobody does that anymore. Okay, we teach how you do that in stats, then we say, please use your calculator. Okay, because it's just ridiculous the amount of work that it takes. Okay, all right, so that wraps up tonight. I'll do that logistic on Thursday, and then we'll start trig. Okay, yay.
I actually like trig more than this. So.
Me too. I do too. I love trig. I'm like the trig geek.
I hate log. I don't like it.
Yes.
How do you clear this?
Yeah, just a second here.